So there's been generally an increase in activity. This relates to the curve I showed you before for Europe temperatures, that there's a lot of variability, and in the case of hurricanes it's quite large, but maybe now we're operating at a different level because the sea temperatures are somewhat higher. And so the overall sea temperatures look like this. This is degrees Celsius, so it's over 1 degree Fahrenheit. The overall sea temperatures have gone up, and you see especially that they've taken off after about 1970 or thereabouts. This is the curve that I like best as an indicator, an integrator of everything that's going on, and it's sea level. We have measurements of sea level in coastal stations and at islands around the world, but in 1992, the French, in conjunction with NASA, put up a satellite called Topex Poseidon, which Topex is short for a topography experiment, where they have a satellite which is in very accurate orbit that is looking down and measuring the surface of the ocean to millimeter accuracy. And so for the first time, we can actually measure the global sea level. And this is what the record is. This is a total record. So the annual cycle is in here as well. Some of these ups and downs, this jaggedness in here is simply related to the fact that there's more snow on the ground in the northern hemisphere in wintertime, and therefore there's less water in the ocean. And so you get a natural annual cycle. This is the El Nino, 1997-98. But the thing is that there's an overall upward trend, and that upward trend is a bit over 3 millimeters per year. And so if you add that up for this period of time, it's actually, sea level has gone up 1.7 inches, about 43 millimeters. That's a rate of 1 foot per century. That's the current rate the sea level is going up. Why is sea level going up? Well, we can measure the changes in temperature in the ocean. We've got measurements of that. And we know that around about 60% of this is because the ocean is expanding, so the sea level is going up. The rest of it we can also measure is from melting glaciers. And so glaciers are melting, and we can estimate that maybe about 1.2 to maybe as much as 1.5 millimeters per year is coming from melting glaciers. And so this is a very good integrator. It's related to warming and also melting of glaciers. And it can't happen from natural variability. This is the evidence from melting glaciers. You may have seen things like this. So this is in Alaska, what it looked like in 1941 and what it looks like now in various other places around the world. Now, it turns out, in places like Alaska, there's actually increases in snowfall because there's more moisture in the atmosphere. But there's even greater melting at the bottom of the glaciers. There are some places around the world where glaciers have increased because of the increase in snowfall. There's always this competition between increases in snowfall and melting in the cases of glaciers. Snow is generally decreasing, but again, it's not a straight line. There's a big drop in the early 1980s, and then it sort of stayed at lower levels in the northern hemisphere. And this is sea ice in the Arctic. I originally had snow at the top and the sea ice down the bottom. I had to move them in order to try and put the 2007 value on here. So this is the IPCC record showing that there's been about a 30% decrease in sea ice in the Arctic since about 1970 in September at its minimum. It's a lot less in the wintertime because the ice is landlocked, and so it can't respond as much. In the summertime, it's not landlocked. And so this is what's happened. But in 2007, there was an extra 20% or over 20% drop, and it's way down here. Greenland is also melting. There's some melt zones on here for 1992 is the pink, and then 2005 is the red. And so Greenland is melting further back. And here's a picture of a part of Greenland, and they have some water rivers and these holes in the ground referred to as a moulin. It's like a big elevator shaft, and they're the size or even bigger than an elevator shaft, where you get torrents of water actually flowing down these moulins in the middle of summertime, and they can go down these crevasse-like features and lubricate the bottom of the glacier, so the glaciers start to move out. Parts of Greenland then start to flow out more rapidly, and it helps the breakup of Greenland. And so If you'd asked glaciologists back in 2001 in the IPCC report, how quickly can Greenland melt, they would have said about 5,000 years. And now the estimate is probably less than 1,000 years because of factors like this. This is my slide to introduce climate modeling. What we do, my institution at NCAR does an enormous amount of this using the biggest and best supercomputers that are available. We try to divide the ocean up into layers and the atmosphere up into layers and replicate all of these processes, the clouds, the radiation, the flow of energy, the flow of water, also in the land, and all of these processes we try to put into climate models. They're approximations to the real world, but they're the best we can do with the computer resources that we have available. And we can use these to do experiments. We can actually, this is one of the neat things about being a scientist, you can play God with these things. And so this is the global mean temperature record, and one of the things we can do with these climate models is to try to replicate what has happened in the climate since 1880, shall we say, based upon estimates as to what has happened to the atmosphere and to the sun. And the main two natural things that have occurred are volcanic eruptions and solar variability. And when we do that, you can see the main spikes down here correspond in the model to volcanic eruptions. So this one here is Mount Pinatubo in 1991. This one here is El Chichon. This one here is Mount Agung. And so these are all volcanic eruptions. And this is the best estimate as to what has happened based upon changes in the sun and volcanoes over time. So there's a bit of warming in here associated with the sun getting a little bit brighter from about 1920 up to around 1950 or thereabouts. Then we can run this also with estimates of what humans have done to the atmosphere by adding greenhouse gases and by adding pollution and changes in ozone, the ozone hole. And that gives you the red curve on here. Oh, by the way, the gray on here, what we did was we ran the model actually several times. And so this is an estimate of the natural variability. If you run the model several times, so there's different weather taking place, but these are the systematic influences. I mean, this is like what happens when you go from one summer to the next. You know summer is different than winter. This is climate, but the weather is quite different. So there are systematic differences, and we can do that with climate models. And so the blue is the average of a number of climate runs, and then the red is another average. What happens when we add the human influences? And you see that these things tend to go along together. They don't quite pick up this peak back in the early 1940s, but they pick up the overall trend in the curves. In particular, they pick up the warming after 1970 when you add in the greenhouse gases and changes in sulfate aerosol and ozone. And the main separation of these curves occurs somewhere around the late 1960s, early 1970s, and that's why I have emphasized to you that this is the time when we think global warming has really kicked in, and what is happening is outside of the realm of natural variability. This is the natural variability that you see here. And in fact, overall, because there's been so many volcanoes in recent times, in fact, here there probably would have been a natural cooling without the increases in greenhouse gases. So this is the thing that gives us confidence. And then here's a prediction now for the next 300 years. This is what it looks like. You have to watch quickly. We're already up to 2100. We're up to 2200. And don't take the actual scale down the bottom too literally. I think it's probably too large. But the patterns are robust from across all models, and you can scale this up and down depending on just what you assume is going to happen to greenhouse gases in the future. And the characteristics are that the biggest warming is in the Arctic. There's much more warming over land than there is over the ocean.